Okay, guys, we move on now. Continue with this part. What we did so far in this section is we learned how to find functions that satisfy this kind of differential equation. dp dt is a constant times p. We recalled on the right side the derivative of exponential function e to a function e to f of x. Y prime is f prime e to the f of x. And we looked at a quick example here. If we have a function, exponential function, this form, we found its derivative and rewrote it. We found that the derivative of the function is the k on the top in the exponent, which is 2 here, times the function itself. So then what we did, we introduced a theorem that allows us to go backwards, to go from the differential equation to the function itself. So that constant in the front that you see goes on the top. Recall very quick, this theorem here we started with a function of x satisfies this equation, dy dx equals ky. We found the function that would satisfy the differential equation based on the previous concept, that whatever function we're going to find is always going to be a constant c, exponential, and k. So that k in the differential equation matches this k in the function, and it depends on the variable. If the variable is x here, you put an x. If it's k, you put, if t, you put t, w, you put w. And we looked at the quick examples here, 3 of them. And now we're going to try to apply this. To do so, we introduce the differential equation dp dt equals kp, or some people write it as p prime is k times p of t. What dp dt? dp dt gives us the rate of growth as time goes by. T is the time. That's what dp dt is called, the rate. And k is a constant. Here we're going to assume it's bigger than 0 for growth, usually less than 0 for decay. So what the equation is saying that the rate is proportional to the population, or to the population size. That's what that is saying. So if t equals 0, we substitute into the boxed equation, and we found p of 0 to be CEK of 0, CE to the 0. E to the 0 is 1, so that gives me the constant, which we're going to call it p of 0. That's called the initial population at time equals 0. That's the initial population. And now we're going to apply it to what we just wrote here. Suppose P of 0 in dollars is invested in an account with an interest compounded continuously. P of 0 means some money, some amount of money in dollars, the initial money is invested. And they said they pay 5% annually as a rate for the money you're trying to invest. So after t years, the balance P per year is growing at the rate dp dt equals 0.05 P. That's all given, and the 0.05 came from 5%. They want us to find a function, as we did in the first half of the section. Find the function satisfying the equation. Okay, we're going to find a function. Find a function means p or p of t It's P of 0 based on the box formula e to the kt. And k here is the number there, the constant. So it's P0 e to the 0.05 t. The second part, part B says, suppose that 1,000 is invested. That's the P0. So P0 is $1,000. What is the balance? So what's P of t after 1 year? So after t equals 1, what is P of 1? Well, from the previous part, we found P of t, P0 e to the 0.05 t. P of 0 is 1,000, e to the 0.05 t. We need to find P of 1. P of 1 is 1,000, e to the 0.05 times 1. Then we need to, so all I did here, I substituted the t with the 1. And then the balance in dollars, if you put that in the calculator, that is about $1,050.27. 27 cents. So after 1 year, the balance will grow from 1,000 to $1,051.27. Now, if $1,000 is invested, so this means the initial amount is still 1,000. How fast is the balance growing? How fast is the balance growing at 1 year or after 1 year or exactly at 1 year? Well, notice what they ask us. They give me P sub 0. They give me the time. How fast is the bounce? How fast? They're talking about the rate. What is the rate? That's what they mean by how fast. What is the rate? So how do we find this out? Rate in this case, they actually want P prime of t is the rate. That's the dB dt. And specifically, they want us to find P prime at 1. What is P prime at 1? Well, we had P of t. We found that it was 1,000 e to the 0.05 t. That was P of t. Now, to find P prime of t, we find the derivative using what we learned last time. 1,000 derivative of e to the e to the function is the derivative of that function, which is 0.05 times itself. So what do we get here? We would like to know what is P prime at 1. It's 1,000 times 0.05 stays the same. All you have to do is substitute T1, 1. Then P prime at 1 is about what? It's about 52.56. So it's about 52.56 per year. So the balance is growing. The balance is growing at the rate of about, you can say the balance is growing at the rate of about $52.56 per year. Okay, we can move on for that. Okay, another example we can go over. Suppose that a company introduces a new computer game in a city using TV advertisements, ads. Surveys show that P% of the target audience buy the game after X ad are broadcast. Satisfying the equation below. P of X equals 100 over 1 plus 47 e to the negative 0.19x. Part A. What percent buy the game without seeing a TV ad? That means when X is zero number of ads. So what do we need to do here? It's very simple, straightforward. What percent? So the P of X, if you read the problem again, it says survey shows that P percent. So the P represents the percent here, the P of X. The P is the percent. Audience buy the game after X ads, X number of ads. So here they said without seeing an ad. So it means X is 0. So that would be P of 0. We need to find P of 0. Means all we have to do is just take that equation and substitute X0. That gives us 100 over 1 plus 47 e to the 0, which is 1. And of course you can go straight forward to the calculator. So it's 100 over 1 plus 47. 100 over 48. What's 100 over 48? It's about 2.08%. So about 2.1%. Let's make it 2.1. 2.1%. Part B. What percentage buy the game after the ad is run 18 times? Eighteen times, this means X is 18. So we need to find P of 18, which is 100 over 1 plus. All we have to do is substitute X equals 18. 47e negative 0.19 times 18. And I strongly encourage you to put this into the calculator and see what you get. If you see if you get the same number as mine, 39.4%. Part C, find the rate of change. P prime of X. Okay, so we need to find P prime of X. So let me write what P of X was. P of X was, on the top was 100, 1 plus 47, e to the negative 0.19 t, or X here. Usually we put t. They want us to find P prime, the derivative for this. This is, again, that's dp dx. To find the derivative, we use quotient rule. Quotient rule says you square the denominator, take the denominator, denominator times the derivative of the numerator minus the denominator itself times the numerator. Derivative of 100 is 0. So you got 1 plus 47, e negative is 19, 0 point this times 0, minus derivative of this is 0 plus 47 times negative 0.19 e to the negative 0.19x, and keep the 100 the same, denominator always stays the same, and you must write it at every single step. The first part is gone. What we need to do here, we need to multiply the negative by negative is positive. You multiply the 47 by this by 100. That gives us 893 e negative 0.19x. Keep the denominator the same. That's all we need to do. Nothing can be simplified more. If I want to add one more part, sketch a graph of the function. Of course, to sketch the graph, you can use a software, free software online called Desmos. Not by hand, to graph the function p of x. So all you have to do is substitute p of x into Desmos, and of course you need to practice a little bit about how to use it. Not difficult. And watch what's going to happen. Here we have x, and this is p of x. If we look back up, go back to the first part, we found p of 0. It was 2.1%. 2.1%. So this means at 0 there's 2 point something. So the graph is going to start here. And this is an exponential one. If you try to plug it into the in Desmos and graph it, notice on the top we have a number 100 in the given p of x. That number, if you draw the line like this, the graph will go, it will grow, wait, let me see, I'm checking it right now. It will grow exponentially like this. It gets close and close to 100. The more you travel to the right side, the more it gets closer and closer to 100. Like this?
Yes. How did you get 893?
Oh, we multiplied, the first part is gone. This negative times negative became positive, right? Because this 0 is nothing. And then what we multiplied the 47 by this, by the 100, those numbers. That gives me 893.
Oh, okay. Makes better sense. Thank you.
Any other questions?
Will you be posting the videos for these two sections?
Based on this question that we did, last one, in general, what we just did, it's a model of a limited growth. So this usually is given by p of t is L divided by 1 plus CE negative K negative LKT. K is positive, L positive. This is a model of limited growth. That's what it is. That's what this is. So the one I just showed you is the equation I give you is similar to this one. So usually the equation or the graph of this would look like this is t in it and this is p of t. There's a line, a horizontal line L here. So p of 0 here, or p sub 0, and then this goes up this way, and it goes this way like that. And in mathematics, this is called the logistic equation or logistic function. There are so many other applications where we can use to model kind of population, especially population growth, and that's what we're focused on. And the reason we call it limited because, as you can see, it's the line L capped it at some point, like it doesn't go beyond that line.